A logic gate is like a simple decision maker that looks at one or more true/false, 1/0 inputs, and gives a true/false output. The truth table lists every possible combination of inputs and the resulting output. Row 1, a 0, B0, AND 0, or 0, not a 1, NAND 1, nor 1, XOR 0, XNOR 1. Row 2, a 0, B1, AND 0, or 1, not a 1, NAND 1, nor 0, XOR 1, XNOR 1. Row 3, a 1, B0, AND 0, or 1, not a 0, NAND 1, nor 0, XOR 1, XNOR 1. Row 4, a 1, B1, AND 1, or 1, not a 0, NAND 0, nor 0, XOR 0, XNOR 0. The Boolean expression is just a compact way to write the rule shown in the table. For example, AND F equals a dot B, both must be true. Or F equals a plus B, any one true. Not F equals not A, flip the value. NAND F equals not a dot B, inverse of A and D. Nor F equals not a plus B, inverse of OR. XOR, F equals an exclusive or B, which equals a not B plus not a B, true when inputs differ. XNOR, F equals not a exclusive or B, which equals a B plus not a not B, true when inputs are the same. These expressions let us treat gates algebraically, just like numbers. Logical identities are the rules of arithmetic for Boolean algebra. They let you shrink a big expression into a smaller, cheaper circuit. Identity, a plus 0 equals A and 1 equals A. Null, a plus 1 equals 1, A and 0 equals 0. Idempotent, a plus A equals A and A equals A. Complement, a plus nada equals 1, A and nada equals 0. Double negation, not nada equals A. Distributive, A and B plus C equals A and B plus A and C and A plus B and C equals a plus B and a plus C. De Morgan, not a plus B equals not A and not B, not A and B equals not a plus not B. Absorption, a plus A and B equals A and A plus B equals A. Example of simplification. Suppose we have F equals A and B plus A and not B plus not A and B. Using distributive law, F equals A and B plus not A and B equals A and 1 plus not A and B equals a plus not A and B. Then applying the absorption rule, F equals A plus B. The original 3-gate circuit becomes a single OR gate. 3-dot universal gate theorem : NAND and NOR as building blocks. The universal gate theorem says that any Boolean function can be made using only NAND gates or only NOR gates. Think of NAND and NOR as the Swiss Army knife of digital logic. You just need one kind of tool to do everything. How to make the basic gates with NAND : not : connect both inputs of a NAND together : a bar equals a NAND A. And : NAND followed by not : a dot B equals a NAND B bar equals a NAND B NAND a NAND B. Or : use De Morgan : A plus B equals the complement of the product of a complement and B complement. Implement the inner knots with NANDs, then NAND the results. How to make the basic gates with NOR : not : tie both inputs of a NOR : a bar equals a NOR A. Or : NOR followed by not : A plus B equals a NOR B bar equals a NOR B nor a NOR B. And : apply De Morgan : A dot B equals the complement of the sum of a complement and B complement. Use NOR for the inner knots and the outer NOR. Practical analogy: imagine you have only red Lego bricks NAND, but need to build a house, a car, and a robot. By stacking the bricks in different ways, you can still build any shape. The same holds for electronic gates. NAND or NOR bricks can be stacked to reproduce any logical function. A Carnot map is a visual grid that helps you spot patterns, groups of ones in a truth table, letting you write the smallest possible Boolean expression. Think of it as a connect the dots puzzle where each dot is a combination of inputs that makes the output true. Step 1. Create the truth table for the target function. Step 2. Plot the ones on a 2, 4, or 8-cell K map. Depending on the number of variables, adjacent cells differ by only one variable: gray code ordering. Step 3. Form groups of 1, 2, 4, or 8 cells that are powers of 2 larger groups. Give fewer literals. Overlapping groups is allowed if it reduces the total count. Step 4. Write a product term for each group. A variable stays in the term only if it has the same value: 0 complement 1 true for all cells in the group. Step 5. Or all product terms together. This is the minimized sum of products expression. Example: suppose f of ABC equals sum m of 0, 2, 3, 5, 7. The three-variable K map yields two groups: a four-cell group covering minterms 2, 3, 6, 7 gives term B, and a two-cell group covering 0, 2 gives term not a not C. The minimal sum of products is F equals B plus not a not C. This uses only one OR gate and NOT gate, far fewer than the original expression. K-maps turn a long algebraic expression into a tiny gate diagram. 5-dot propagation delay, fan-out, and power characteristics. When a gate changes its output, it does not happen instantly. Propagation delay, TP, is the time between an input change and the resulting output change. Imagine a row of dominoes. The first domino input falls, and after a short pause, the last domino output falls. The delay depends on the gate's internal capacitance and the strength of its transistors. Typical values: TP sub ND approximately 5 to 10 nanoseconds, TP sub OR approximately 5 to 10 nanoseconds, TP sub NOT approximately 2 to 5 nanoseconds, CMOS. Cumulative delay: if you cascade 3 gates, total delay approximately sum of individual delays. This matters in high-speed circuits, for example CPUS. Fan-out is how many identical gates a single gate can drive while still meeting timing specifications. Each gate presents a load input capacitance. Think of a water faucet, the driver feeding many hoses, the loads. Too many hoses reduce water pressure, which is analogous to signal integrity. In CMOS, a typical fan-out is 4 to 10. If you need to drive more, use a buffer, an extra gate that provides extra current. Power consumption has two components: static leakage power, small current that flows even when inputs are steady, and dynamic power, energy spent charging and discharging the gate's load capacitance each time the output toggles. Approximate formula: P sub dyne equals alpha times C sub L times V sub DD squared times F, where alpha is the switching activity, C sub L is load capacitance, V sub DD is supply voltage, and F is switching frequency. Lowering supply voltage or reducing switching frequency saves power, which is why modern chips use multiple voltage domains and clock gating. Explanation: 6 typical examination problems: design, simplify, and convert logic functions. Problem 1, SOP design. Given f of a, b, c, d equals sigma m of 1, 4, 6, 9, 11, 13. Build the truth table. Plot a 4-variable K maps. Form groups, for example, a 2-cell group for 1 and 5 gives not a B, not C, D, etc. Write the minimized sum of products. Finally, draw the gate diagram using only AND or NOT gates. Problem 2, NAND only implementation. Take the sum of products from problem 1 and convert every AND or NOT into NANDs using the universal gate formulas, see topic 3. Count the total number of NAND gates and compare with a mixed gate implementation. Problem 3, delay calculation. A circuit consists of a NOT gate with propagation time 3 nanoseconds feeding an AND gate with 7 nanoseconds, which in turn drives a NOR gate with 8 nanoseconds. Calculate the worst-case propagation delay from the primary input to the final output. Solution: 3 nanoseconds plus 7 nanoseconds plus 8 nanoseconds equals 18 nanoseconds. Problem 4, algebraic simplification. Simplify f equals a plus b times not a plus c times not b plus not c. Apply distributive and absorption identities step by step. The final reduced expression is f equals a not b plus b not c. This shows how a 3-gate product can become just 2 AND OR terms. These kinds of questions appear in digital design exams. Mastering truth tables, K-maps, and universal gate conversions gives you a reliable toolbox. 7. Algebraic derivation of exclusive or an exclusive NOR using basic gates. Exclusive OR is true only when the inputs differ. Starting from the definition, you can build it with AND, OR, and NOT. A XOR B equals open parenthesis A and not B close parenthesis or open parenthesis not A and B close parenthesis. Step-by-step derivation. 1. Write the truth table for exclusive or 1 when 0, 1 or 1, 0. 2. Notice each true row contains one variable true and the other false. 3. Express those rows as product in terms, a not B and not a B. 4. Combine the two product terms with OR. Exclusive NOR is the complement of exclusive, or that is true when inputs are the same. Algebraically, A XNOR B equals not open parenthesis a XOR B close parenthesis equals open parenthesis A and B close parenthesis or open parenthesis not A and not B close parenthesis. This uses the same idea, but now the true rows are 0, 0, and 1, 1, both represented by n terms that are then or D. Implementation with NAND only using the universal gate. Build not with NAND as described earlier. Construct the two and terms using NAND then NAND, that is NAND followed by a NOT. Finally NAND the two results together and NAND the output with itself to get the OR. The same pattern works for exclusive NOR, except you add an extra NAND not at the very end to invert the exclusive or result. These algebraic forms make it clear why exclusive OR needs more gates than a simple, and OR, it is essentially 2 ins plus an OR plus optional inversion for exclusive NOR.